Hi, I'm continuing my discussion of the Collatz conjecture, also known as the 3x plus 1 problem. This is, I think, the 7th video in the series, and I'm continuing my discussion of loops. And here I have an example of a input-output for 3x plus 9. So I'm looking at Collatz type sequences where n is greater than 1. And the reason I'm doing this is to prove by counter argument or counter example why 3x plus 1 does not loop as these other formulas do. So this is 3x plus 9. And you can see the input-output here. It's a compressed table. I've eliminated the three congruence classes for input and output, and I'm just showing them by letter. It doesn't really matter. The most interesting or important thing about this, certainly not the most interesting, is that input 9 goes to output 9. And you're always going to get this. Whatever the value of n is going to be this zero operation. Nothing changes. It's equivalent to 1 in 3x plus 1, which is the trivial loop, and I'm simply eliminating the even numbers. So in the trivial loop for 1, it's 1, 4, 2, 1, and in this one it's going to be a little bit different. It's going to be 3 times 9, 27, plus 9, 36, and then you have that 18, 9. And so that's very easy to demonstrate. So with input 27, you can see the cycle 9, 36, 18, 9. And if you choose the odd-only version, you're just going to see 99999. What's very interesting is that we have this symmetrical inverse operation on either side of the 0 point. So we have input 3, output 9, that's plus 6, input 5, output minus 1, minus 6. So these two operations cancel each other out, and similarly on the other side of the 0 we have minus 12, plus 12. And so the significance of this is, and I'm going to make the statement that all loops other than the trivial loops, in other words, all complex loops, occur because of these inverse relationships. Now here I have set up a table that's actually putting the different odd ends side by side, beginning with 3x plus 1, missing out on 3x plus 3, which I think is rather boring, plus 5, plus 7, plus 9, plus 11, and so on. And you see here this very regular progression, of course, of the zero input, the non-operational 0 to 0, n to n operations. What I'm going to look at quickly is the loop for 11, and this is the loop described here: 27, 23, 3, 5, 13, 25, 43, and so on, back to 5. Okay, you can plot this out on this table. So starting here, 5, 13, 13, 25, 25, 43, so on to 31, 5. Back to 5, we've closed the loop.